Imagine trying to build a house while blindfolded, wearing thick gloves, and floating in zero gravity. Now multiply that complexity by 1,000, and you'll begin to understand the engineering marvel that is ISS construction. The International Space Station isn't just humanity's greatest construction project. It's a 450-ton puzzle assembled piece by piece while hurtling through space at 17,500 miles per hour. How do you connect modules the size of school buses when a single mistake could spell disaster for the entire crew? The International Space Station is one of the most ambitious engineering projects ever attempted by humanity. It did not come together overnight. In fact, it took over a decade of carefully planned missions, hundreds of astronauts, thousands of engineers and technicians back on Earth, and a level of international cooperation that had never been tried before in space. ISS is not just floating aimlessly above Earth. It orbits our planet at an incredible speed, about 20 times the speed of sound, circling Earth once every 90 minutes. At that pace, astronauts on board witness 16 sunrises and 16 sunsets every single day. But building something so massive, so precise, and so fragile at such speeds required solving enormous challenges. Think about it. Every piece of the station, from the smallest bolt to the largest laboratory module, had to be launched separately aboard rockets and space shuttles. Once in orbit, they had to be maneuvered with robotic arms, carefully aligned and locked into place by astronauts who were often working outside the station in bulky spacesuits, tethered only by cables while the Earth spun thousands of kilometers beneath them. Construction of the ISS was only possible through meticulous planning. Engineers on the ground spent years designing how each module would fit together, which mission would bring it up, and how astronauts would physically connect one part to another while floating in microgravity. Each step was tested and rehearsed countless times in huge training pools on Earth, where astronauts practiced underwater to simulate weightlessness. The process also relied heavily on mission control centers in the United States, Russia, Europe, Japan, and Canada. These teams monitored every maneuver, every spacewalk, and every robotic operation, making sure everything was done safely and in the correct sequence. Communication between space and ground had to be constant, because even the smallest error could damage a module or jeopardize the safety of the crew, piece by piece. Mission after mission, the ISS slowly grew from a single Russian-built module called Zarya, launched in 1998, into the sprawling orbital outpost we know today. By the time construction was officially declared complete, more than 10 years later, the station had become the largest human-made structure in space, stretching the length of a football field and weighing over 400 tons. But more than just size, the ISS represents international cooperation on a scale humanity had never seen in space exploration. The United States, Russia, Europe, Japan, and Canada all contributed modules, robotics, and crews. Without this global partnership, building the ISS would have been impossible. The assembly of the station is not just about hardware and technology. It's also a story about trust between nations, coordination between thousands of people, and the shared belief that working together in space would push humanity forward. Every bolt that was fastened, every cable that was connected, and every astronaut who floated through the vacuum to add a new piece helped turn the dream of a permanent space station into reality. This overview only scratches the surface of what it took to build the ISS. To really understand how it happened, we need to go deeper into the details. The different modules, the docking systems, the robotic arms, and the specific missions that slowly transformed a handful of components into a fully functional orbital laboratory. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. To understand how the International Space Station was built, we first need to understand what it actually is. At its core, the ISS is not one single spacecraft, but a collection of interconnected pieces. most of them cylindrical modules that together form a functioning space habitat. These modules are pressurized, meaning they are filled with air that astronauts can breathe and are kept at a temperature and pressure similar to what we experience on Earth. Inside, they serve as living quarters, laboratories, storage rooms, and workspaces. Beyond these modules, the ISS also has large truss structures, which act like the station's backbone. Attached to these trusses are the station's massive solar arrays, providing electricity for all onboard systems and radiators that get rid of excess heat. Think of the trusses as both the support beams and the utility lines of the ISS, keeping everything powered, cooled, and stable. Now, when astronauts live and work on the station, they can't use directions like up and down. After all, in orbit, there's no gravity pulling you toward the floor. Instead, astronauts rely on a special vocabulary to describe orientation. The front of the station, which always points forward in its orbit around Earth, is called forward. The opposite end is aft. The left-hand side, from the crew's perspective facing forward, is port, and the right-hand side is starboard. Then we have zenith and nadir. Zenith refers to the side of the station pointing away from Earth, toward open space. Nadir is the side facing down toward Earth. These words may sound unusual, but for astronauts, they're absolutely essential. Without gravity to orient yourself, clear and consistent terminology is the only way to make sure everyone knows exactly where things are located and which direction to move. This language becomes especially important during complex tasks like spacewalks or robotic arm operations. Imagine two astronauts floating outside the station, one holding onto a piece of equipment while the other controls the canadarm from inside. If mission control says, "Move the payload to the port side and rotate toward nadir," everyone needs to instantly visualize that direction without confusion. Inside the station, the pressurized modules are where the astronauts spend nearly all their time. Each module is connected to others through docking or berthing ports, forming a chain of habitable compartments. Once a new module is added, astronauts can move freely between them as if walking through hallways, though of course they are floating in microgravity. These connections also allow for crucial systems, electricity, data, oxygen, and even water, to pass between modules, keeping the entire station functioning as one. Over time, as new modules were added, the ISS grew into a structure roughly the size of a football field. But in the early years, when construction had just begun, it was a much smaller, simpler station. Understanding how its structure is organized and how astronauts talk about it helps us make sense of the missions that slowly transformed the ISS from just two modules into the massive laboratory orbiting above our heads today. So when we hear terms like "attach this to the nadir port" or "relocate the docking adapter to the forward side," it's not just jargon. It's the precise language that keeps astronauts coordinated and safe while they build and maintain one of humanity's greatest engineering achievements. The International Space Station is often described as one spacecraft, but in reality, it's made up of two major sections, each built by different countries using different engineering approaches and even different design philosophies. These are the Russian Orbital Segment, or ROS, and the United States Orbital Segment, or USOS. Let's start with the Russian Orbital Segment. This part of the station was the very first to reach orbit. The module called Zarya, launched in 1998, was built by Russia with funding from the United States, and it provided the foundation for everything that followed. Over time, additional Russian modules were added, such as Zvezda, which serves as a living quarters and control center, and smaller research and docking modules that support visiting spacecraft. The Russian segment is known for its rugged, compact design. These modules are narrower, built to fit on top of Proton rockets, and are packed with life support systems, navigation controls, and engines that can adjust the station's orbit when needed. In fact, to this day, the Russian side provides most of the propulsion to keep the ISS from gradually falling back into Earth's atmosphere. Now, compare that with the United States Orbital Segment, or USOS. This part of the station is far larger and more international in scope. It includes modules built not only by NASA, but also by Europe's ESA, Japan's JAXA, and Canada, which contributed robotics. The USOS is where you find the largest laboratories like Destiny, the American lab, Columbus, the European lab, and Kibo, the Japanese module with its own exposed platform for experiments directly in space. These modules are wide, brightly lit, and designed to feel a bit more spacious than the tighter Russian compartments. But here's the interesting part. The two segments were never designed to be fully compatible. The Russian side uses one type of docking system and engineering standard, while the USOS relies on something called the Common Berthing Mechanism, or CBM. This system allows large modules to be joined together through robotic operation, with bolts and seals locking them tightly into place. The Russian docking ports, on the other hand, are smaller, designed for automated spacecraft like Soyuz and Progress. To make these two different systems work together, engineers had to develop special connectors called Pressurized Mating Adapters, or PMAs. These adapters act as translators between the Russian hardware and the American hardware, creating a pressurized tunnel where astronauts can pass between the two segments. Without the PMAs, the ISS would essentially be two separate stations flying side by side. This split personality is one of the unique features of the ISS. Each segment reflects the traditions and priorities of its builders. The Russian modules are compact, practical, and heavily focused on station keeping and reliability. The USOS, meanwhile, emphasizes scientific research, international partnership, and expandability. Together, they balance each other, one side providing propulsion and stability, the other offering space for science and cooperation. It's worth remembering that building these two different systems into one functioning station wasn't just a technical challenge, it was also a diplomatic one. Russia and the United States had to trust one another deeply, especially in the years after the Cold War, to connect their spacecraft and allow their crews to live and work side by side. Every time astronauts float from the USOS into the ROS, they're moving across not just a technical boundary, but a political one. And yet, up there in orbit, it functions seamlessly as one station. One of the most remarkable aspects of the International Space Station is how its individual pieces, launched separately on rockets from different countries, come together in orbit to form a single unified spacecraft. This process depends on a highly sophisticated system known as the Common Berthing Mechanism, or CBM. Unlike a simple docking, which is often just one spacecraft latching onto another, the CBM is designed for permanent connections between modules. Picture it like a high-tech version of snapping Lego blocks together, except each block is the size of a bus and floating 400 kilometers above Earth. Here's how it works. When a new module arrives, usually carried into orbit by a space shuttle in the past, or a cargo vehicle more recently, the station's robotic arm carefully positions it next to the port where it will be attached. The CBM consists of two main parts, an active side and a passive side. The active side has motorized latches and mechanisms, while the passive side is essentially a strong frame designed to be gripped. First, a set of capture latches reach out and pull the two sides of the mechanism into alignment. Once everything is lined up perfectly, 16 powerful bolts drive into place, locking the modules together with an airtight seal. This forms what astronauts call a vestibule, a small tunnel-like space between the two modules. But the vestibule isn't ready to use right away. Initially, it's just an empty cavity. Astronauts must carefully pressurize it with air, making sure the seals hold and there are no leaks. Afterward, the crew begins the vital process of connecting all the station's life-supporting systems. That means installing oxygen lines, electrical cables, water pipes, and data connections. Without these links, the new module would be just a sealed container floating in space. With them, it becomes a fully integrated part of the station's living and working environment. Only once everything is checked, tested, and stable, do astronauts open the hatches and float through for the first time. Imagine the excitement of that moment, entering a brand new room in orbit, built on Earth, launched through fire and thunder on a rocket. and now permanently attached to your home in space. Each time a module was added, the ISS grew larger, more capable, and more alive. What's fascinating is that this process had to be repeated many times over the course of more than a decade. Every laboratory, every node, every connecting hallway was attached using the CBM, turning individual spacecraft into the sprawling orbital outpost we see today. The system was designed to be modular and expandable, ensuring that as technology advanced and international partners contributed more components, the station could keep growing. It's also worth noting how much precision and teamwork is required for these connections. On Earth, heavy machinery and cranes do the lifting. In space, astronauts rely on robotic arms, remote control, and their own careful movements while floating in microgravity. Even with the CBM's 16 bolts doing the heavy securing, the entire process is a delicate ballet of engineering and human coordination. The end result is extraordinary. Thanks to the CBM and the careful integration work by astronauts, the ISS today feels like one continuous spacecraft. Crews can float seamlessly from an American lab into a European one, then into a Japanese module, and even cross over into the Russian segment. It's a constant reminder that the station is more than just a machine. It's a global collaboration, held together by bolts, air pressure, and a vision of working together in space. When we talk about the construction of the International Space Station, there's one vehicle that stands out as absolutely essential: the Space Shuttle. Without it, the ISS as we know it could never have been built. The shuttle was unique in many ways, but its most important contribution to the station was its payload bay, a cavernous cargo hold about 18 meters long and 4.6 meters wide. This space was large enough to carry entire station modules, each the size of a small bus, into orbit. No other rocket at the time could transport objects of that size and weight. When a shuttle launched with a new piece of the ISS inside, it was essentially carrying the next building block of humanity's home in space. Once in orbit, the shuttle would carefully maneuver and dock with the growing station. This was often done using Pressurized Mating Adapters, or PMAs, which acted as connectors between the shuttle and the station's docking ports. Once docked, the shuttle became not just a delivery vehicle, but also a temporary extension of the station itself, a place where astronauts could live, sleep, and prepare for spacewalks. Those spacewalks, officially called EVAs, were another crucial part of the shuttle's role. Shuttle crews would often perform multiple EVAs during a single mission to install new modules, connect power cables, or bolt trusses into place. Picture astronauts floating outside, tethered to the station, using specialized tools to secure enormous structures while Earth glides silently below. These were some of the most complex construction projects ever carried out in space, and the shuttle provided both the crew and the equipment to make them possible. But the shuttle didn't just carry people and parts, it also carried a powerful helper, the Canadarm robotic arm. This 15-meter robotic arm could reach into the shuttle's payload bay, grab massive modules weighing up to 16 tons, and maneuver them with millimeter precision. Astronauts inside the shuttle used joysticks and cameras to guide the arm, carefully handing off modules to the station's own robotic systems or holding them in place while spacewalkers secured them. Without Canadarm, moving such heavy and unwieldy pieces in microgravity would have been nearly impossible. Over the course of more than a decade, the shuttle fleet, Columbia, Challenger, Discovery, Atlantis, and Endeavour, delivered most of the station's largest components: nodes, laboratories, trusses, solar arrays, docking adapters. All of them rode into orbit inside the shuttle's payload bay. Each mission added a new piece to the puzzle, gradually transforming the ISS from just a pair of connected modules into the massive football field-sized outpost we see today. The shuttle also served as a workhorse for repairs and upgrades. For example, when solar arrays needed installation or when critical systems had to be swapped out, shuttle missions provided the manpower, tools, and logistics to get the job done. Crews trained extensively on Earth, rehearsing the exact spacewalks they would later perform, and then executed those same steps in orbit with remarkable precision. In many ways, the shuttle was more than a spacecraft. It was a construction crane, moving van, and workshop all rolled into one. It gave humanity the ability to bring up giant modules, position them with robotic precision, and then send astronauts outside to bolt everything together. Without the shuttle's versatility, the modular, expandable design of the ISS would have remained only an idea on paper. Even though the shuttle program retired in 2011, its role in building the ISS cannot be overstated. Every time astronauts float through a laboratory or pass a truss holding the solar arrays, they are moving through structures that were carried into orbit on the wings of the shuttle. It was the backbone of early ISS construction, and its legacy is permanently built into the station itself. The story of the International Space Station's construction truly begins with STS-88, a space shuttle mission that launched in December 1998. This flight marked the very first time the shuttle delivered a major component of the ISS into orbit and physically joined it with another module already waiting there. It was the start of something extraordinary, the birth of humanity's permanent outpost in space. At the time, the station consisted of only a single module, the Russian-built Zarya, launched a few weeks earlier. Zarya was a functional powerhouse. It carried batteries, fuel tanks, and the ability to provide power and propulsion. But it wasn't designed for living or long-term operations. For the ISS to become a true international project, Zarya needed a partner, the American-built Unity module. Unity was the first U.S. contribution to the station, and it was carried up inside the payload bay of Space Shuttle Endeavour. Attached to either end of Unity were two crucial connectors, Pressurized Mating Adapter 1, PMA1, and PMA2. These adapters would allow Unity to link not only to Zarya, but also later to other incoming modules, serving as the first hub of the growing station. Once in orbit, the task of joining Unity with Zarya began. This was no small feat. Endeavour's crew relied on the Canadarm robotic arm, operated from inside the shuttle, to carefully grapple Unity and position it near Zarya, with shuttle thrusters firing in tiny, precise bursts to keep everything steady. The two modules were slowly brought together. At the moment Unity's PMA connected with Zarya's docking port, the International Space Station officially became more than one module. It became a structure, the very beginning of what would eventually grow into a vast orbital complex. But docking the two modules was only part of the mission. The crew also had to make sure Zarya and Unity could actually function as one. This required two complex spacewalks, or EVAs. During these excursions, astronauts Jerry Ross and Jim Newman floated outside the shuttle to connect power cables, data lines, and communication antennas. These connections were the lifelines that allowed the Russian and American systems to begin working together. Without them, Zarya and Unity would have been just two sealed cans floating side by side, working in bulky spacesuits, with Earth spinning silently below. The astronauts bolted down equipment, connected umbilicals, and deployed antennas that would let ground control keep in constant contact with the young station. It was delicate, exhausting work, but it marked the first hands-on construction effort of the ISS in orbit. After the spacewalks were complete, came another historic milestone. For the first time, astronauts floated through the hatches and entered the ISS itself. At this point, the station was uninhabitable. There was no permanent crew, no running water, and no oxygen system. It was cold, silent, and empty. But as the astronauts explored Unity and Zarya, they knew they were inside the first rooms of what would become a continuously inhabited laboratory in space. STS-88 set the tone for the next decade of ISS assembly. It showed that modules from different countries could be joined successfully, that astronauts could perform complex wiring and assembly tasks in orbit, and that the vision of a global station was truly achievable. Every mission that followed built on the success of this first critical step. Looking back, December 1998 may not have felt like a giant leap at the time, just two modules bolted together in the vacuum of space. But in hindsight, It was the beginning of one of humanity's greatest engineering triumphs, a station that would grow, thrive, and serve as a home in orbit for decades to come. By early 2001, the International Space Station had already grown beyond its first 2 modules. Several new pieces were in place, and for the first time, a small permanent crew had begun living on board. But the station still lacked something essential: a fully equipped laboratory where astronauts could conduct cutting-edge research. That all changed with STS-98, a Space Shuttle Atlantis mission in February 2001. The centerpiece of this mission was the Destiny Laboratory Module, the first major U.S. science lab in orbit. Destiny wasn't just another cylindrical room to add living space. It was designed as a state-of-the-art research facility, packed with racks, systems, and the infrastructure to support experiments in biology, physics, medicine, and earth science. This single module transformed the ISS from a growing construction project into a true international laboratory. But installing Destiny wasn't as simple as snapping it into place. The shuttle docked with the station at PMA-3, which had been temporarily attached to the underside of Unity. To make room for Destiny, the crew had to carefully relocate PMA-2, moving it from the front of Unity over to the Z1 truss structure. This was a delicate dance, requiring the precision of the Canadarm robotic arm and careful coordination between shuttle pilots and mission control. Once the docking ports were clear, it was time for the big moment. Using the Canadarm, astronauts slowly lifted Destiny out of Atlantis's payload bay, rotated it 180 degrees, and maneuvered it into position. Inch by inch, the lab was guided toward the forward berthing port of Unity. After hours of careful alignment, latches pulled the 2 modules together, and Destiny became a permanent part of the station. The very next day, the crew opened Destiny's hatch for the first time. Floating through its pristine interior, the astronauts entered what would soon become the heart of American research in space. The lab contained racks lining its walls, each designed to hold equipment, experiments, or life-supporting systems. It was bright, spacious compared to earlier modules, and filled with promise. For the astronauts, stepping inside Destiny was like watching the ISS take a leap forward in purpose. But the mission was far from finished. Over the course of 3 demanding spacewalks, the crew worked outside the station to complete Destiny's installation. They bolted on external hardware, connected crucial power and data cables, and ensured the module was fully integrated into the growing orbital outpost. Each EVA required hours of concentration, as astronauts carefully maneuvered themselves with tethers and foot restraints while Earth sped by beneath them. When the final connections were made, the ISS had gained more than just another room. It had gained its scientific core. Destiny gave the United States and its partners the ability to carry out long-term research in microgravity, with applications ranging from medical breakthroughs to new materials and technology. It was also designed to support future modules, serving as a central hub for expansion on the U.S. side of the station. STS-98 wasn't only about hardware, it was about vision. With Destiny in place, the ISS officially became a laboratory, not just a construction site. For the first time, the promise of international cooperation and scientific discovery in space began to look real. The lab that Atlantis delivered in 2001 continues to operate today, a reminder of how every shuttle mission added not just a module, but a new capability to the station. Just a few months after the installation of the Destiny Laboratory, the International Space Station took another major step forward with STS-100, a mission flown by Space Shuttle Endeavour in April 2001. This flight was unique because it delivered a game-changing piece of technology, the Canadarm2, a robotic arm that would become a permanent and indispensable tool for the ISS. Canadarm2 was no ordinary robotic arm. It was an upgraded, much more powerful version of the original Canadarm, which had previously been mounted on the shuttle itself. Unlike its predecessor, Canadarm2 could remain on the station permanently, allowing astronauts to move massive modules, perform maintenance, and assist with assembly even when the shuttle was not present. Its design included latching end effectors, which could attach to any power and data grapple fixture located anywhere on the station, giving it incredible flexibility to move along the truss and handle heavy objects in microgravity. Installing Canadarm2 was a precise and intricate operation. The arm arrived on a special pallet inside Endeavour's payload bay. Using the shuttle's original Canadarm, the crew lifted the pallet out of the bay, carefully positioning it above the Destiny module. Once in place, the astronauts began unfolding and assembling Canadarm2 itself. It was like watching a giant mechanical spider slowly stretch its legs, each movement deliberate and controlled to avoid damaging any components. After assembly, Canadarm2 performed its first test movement, slowly lifting itself and connecting to a grapple fixture on Destiny. This marked the first time the station had a robotic arm that could move independently and remain in orbit permanently. To celebrate, the astronauts executed what has since been called the first Canadian handshake in space. Canadarm grasped the Raffaello pallet and handed it back to the shuttle's Canadarm, a symbolic and practical demonstration of collaboration between the two robotic systems. Both arms, designed and built in Canada, work together seamlessly in microgravity, showcasing the power of international engineering. Alongside Canadarm2, STS-100 also delivered the Raffaello Multi-Purpose Logistics Module, which was temporarily attached to the station to transport supplies, equipment, and scientific experiments. Raffaello allowed astronauts to transfer cargo efficiently, reducing the need for multiple supply runs. Its integration with Canadarm2 was critical, as the robotic arm could maneuver it into position, hold it steady, and assist with unloading. This mission was a turning point for the ISS because it gave the station a tool that would be used for nearly every major construction task going forward. Future modules, trusses, and even visiting spacecraft could now be moved, installed, and maintained with a level of precision impossible without a permanent robotic arm. Canadarm2 effectively became the station's mechanical hands, capable of lifting, rotating, and supporting massive components, while astronauts floated nearby, guiding it or performing EVAs. STS-100 demonstrated the synergy of human and robotic effort in orbit. Astronauts controlled Canadarm2 from inside the station, while mission controllers on Earth monitored operations in real time. Every movement required careful coordination, yet by the end of the mission, Canadarm2 was fully operational. Raffaello had been successfully installed and unloaded, and the ISS had gained both a permanent logistics capability and a versatile robotic assistant, a true leap forward in its construction and operational capacity. By mid-2001, the International Space Station had grown into a functional orbital outpost, but there was still a critical missing piece: the ability for astronauts to perform spacewalks directly from the station itself, independent of the shuttle. This capability arrived with STS-104, flown by Space Shuttle Atlantis in July 2001, which delivered and installed the Quest Airlock. Quest was designed specifically to allow astronauts to don their spacesuits and exit the station safely. Unlike previous EVAs, which could only be conducted from the shuttle's payload bay, Quest provided a permanent gateway for construction, maintenance, and scientific tasks. The airlock was installed on the starboard side of the Unity module, a location carefully chosen to integrate seamlessly with the existing station. Structure. Installing Quest required the precision of Canadarm2 and the skill of astronauts performing extravehicular activities, EVAs. Using the robotic arm, the crew lifted the massive airlock out of Atlantis's payload bay, positioned it carefully alongside Unity, and slowly attached it to the module's berthing port. The astronauts then floated outside to guide Quest into its final position, securing it with bolts and connecting power, data, and life support systems. One of the key components of Quest is its set of high-pressure oxygen and nitrogen tanks. These tanks supply the air astronauts breathe inside their spacesuits during spacewalks. Once outside, Canadarm2 was used to lift these heavy tanks into place, while astronauts guided them into position, ensuring a secure and functional connection. This integration meant that the station could now support multiple EVAs without relying on shuttle resources. Quest is divided into two main sections, the crew lock and the equipment lock. The crew lock is the part that astronauts enter in their spacesuits. It is depressurized to allow them to exit safely into the vacuum of space. The equipment lock, on the other hand, serves as a staging area for tools and hardware needed for repairs or assembly tasks. This dual design makes Quest extremely versatile, providing both a safe airlock and a workspace for preparation. Another interesting feature of Quest is the orientation of its hatch. Unlike most station hatches, which can be oriented in any direction depending on the module's design, Quest's hatch opens toward Earth, giving astronauts their first breathtaking view of the planet directly below as they step outside. It's a visual reminder of how high and far from home they are, floating in microgravity while tethered only to the station. The successful installation of Quest marked a pivotal moment in ISS construction. No longer were spacewalks tied to shuttle missions. Astronauts could now carry out assembly, maintenance, and science tasks directly from the station. It significantly increased the station's operational independence, allowing crews to continue building and expanding the ISS between shuttle flights. STS-104 combined robotic precision, careful EVA planning, and international engineering collaboration. With Quest in place, the station gained a permanent gateway to the vacuum of space, a critical tool that would enable all subsequent construction, from trusses and solar arrays to docking ports and scientific modules. The station was becoming not just a laboratory, but a fully functioning habitat and construction platform in orbit. The construction of the International Space Station was nothing short of an engineering marvel, and the early shuttle missions provide a clear picture of how humanity transformed an ambitious blueprint into a functioning orbital outpost. By examining STS-88, STS-98, STS-100, and STS-104, we can see the painstaking process by which the station was assembled piece by piece. Each module, adapter, and system carefully integrated into a larger, coherent structure. STS-88 demonstrated the delicate choreography required to join Russian and American modules in orbit for the first time. Unity and Zarya, connected through pressurized mating adapters, became the first step in uniting two nations' engineering philosophies into a single station. The use of Canadarm and carefully planned EVAs highlighted the interplay between astronauts and robotics, and it set the standard for all subsequent assembly work. Even entering the station for the first time, though it was uninhabitable, represented a symbolic milestone. The first rooms of humanity's permanent presence in space were ready. Then came STS-98, delivering the Destiny Laboratory. This mission illustrated how the ISS was evolving from a construction site into a fully functional science laboratory. The relocation of PMA-2, the careful berthing of Destiny, and the 3 spacewalks required for full installation underscored the precision and planning involved in assembling modules in microgravity. Destiny became the hub for experiments, enabling long-term research that could only be conducted in orbit, a clear leap forward in the station's capabilities. STS-100 introduced Canadarm2, the permanent robotic arm, along with the Raffaello logistics module. Canadarm2 was a game-changer, capable of moving heavy modules and equipment independently, making construction and maintenance far more flexible. The first Canadian handshake, when Canadarm2 handed cargo back to the shuttle's original Canadarm, symbolized both technical ingenuity and international collaboration. These robotic systems became the station's mechanical backbone, performing tasks that would have been impossible without them. Finally, STS-104 delivered the Quest Airlock, granting the station its own spacewalk capability. Astronauts could now exit the station directly to perform maintenance, install new modules, or conduct experiments outside the station. High-pressure oxygen and nitrogen tanks, maneuvered with Canadarm2 and astronauts' guidance, provided life support for EVAs, and the design of the crew lock and equipment lock made these operations safe and efficient. Quest's installation also demonstrated the seamless integration of robotics and human skill, giving the ISS operational independence from the shuttle. Taken together, These 4 missions illustrate the foundational principles of ISS Assembly: careful planning, precision engineering, robotic assistance, and above all, international teamwork. Each module added new capability, each spacewalk tested human skill and endurance, and each robotic operation expanded what astronauts could do in orbit. The station didn't appear fully formed. It was meticulously constructed, one piece at a time, with constant support from mission control on Earth and coordination among multiple space agencies. Today, the ISS stands as a fully operational laboratory and habitat, a sprawling testament to decades of collaboration and technological achievement. Its very existence is a reminder that building in space requires patience, ingenuity, and cooperation on a scale never seen before. These early shuttle missions laid the groundwork, creating a resilient platform that continues to support science, exploration, and international partnership. From Unity and Zarya to Destiny, Canadarm2, and Quest, every module, every connection, and every carefully executed spacewalk contributed to the station we see today, a true home for humanity in orbit. And that's how the International Space Station came together. Module by module, bolt by bolt, spacewalk by spacewalk, with astronauts and robotic arms working hand in hand across continents. From the first connections of Unity and Zarya to the installation of Destiny, Canadarm2, and Quest, these missions show the incredible planning, skill, and international cooperation required to build humanity's home in space. The ISS stands today not just as a technological marvel, but as a symbol of what we can achieve when nations collaborate, scientists innovate, and explorers push the boundaries of what's possible. Every bolt tightened, every cable connected, and every module joined has paved the way for decades of scientific discovery and human presence in orbit. Thanks for watching. If you enjoyed this deep dive into how the ISS was built, don't forget to like, subscribe, and hit the notification bell so you can explore more stories about space, science, and the incredible engineering behind the missions that push humanity beyond Earth. If you found this journey through hidden science, cosmic secrets, and potential alien infrastructure as mind-blowing as we did, make sure to subscribe and hit the notification bell. Don't miss future explorations into the universe's deepest mysteries, because some secrets are just waiting to be uncovered.